This is the third lecture for Chapter 8, which Chapter 8 is introducing acids and bases. This lecture is going to cover strong acids and bases. So first of all, there are strong and weak acids and bases. So the difference between these strong acids and bases dissociate completely. So when they get in solution, they break apart 100% into their individual ions. So strong acids will be dissociating into H plus and their anion, their negative charge. Strong bases will be dissociating into their cation, their positive charge, and then OH minus, hydroxide ion. So 100% of the time, completely break apart. Weak acids dissociate, but only partially. So a smaller percentage than 100, somewhere between, 1 and, well, I guess officially 99%. Most weak acids and bases dissociate between like 2 and 10%. So that would mean that of all of the molecules, only, between 2 and 10% of them break apart into their cation and anion. The other amounts of the weak acids and bases stay bonded where the cation and anion do not dissociate. So for the strong acids, there are officially, according to this textbook, 6 strong acids: hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, perchloric acid, and then sulfuric acid. The first 5 are considered monoprotic acids because they only have one proton. There's one H plus. So as they're strong acids, that means these 6, these first 5, when they dissociate, they break apart into H plus and then their anion, their negative charge. So this is 100% of the time. That's why in all of these equations here, you'll see the arrow is written just left to right. It's not an equilibrium arrow. The reactants become products completely. So the expression I have there, that I used nitric acid as the example. Nitric acid, the molarity of nitric acid is going to be equal to the molarity of H plus and the molarity of NaNO3 minus nitrate, because nitric acid, HNO3, is going to completely break apart into H plus and NO3 minus. None of them will be left bonded. But then at the end I wrote equals hydronium ion, H3O plus. If you remember from the last, I think, lecture of Chapter 8, we're going through water. When hydrogen ion, H plus, is around water, when it's in an aqueous solution, that hydrogen ion and the water bond to become this hydronium ion. So the best way to express H plus, as long as it's aqueous, is actually H3O plus. So all the way through this, we can assume for a strong monoprotic acid, the molarity of that strong acid is equal to the molarity of the hydronium ion, because the strong acid dissociates completely. So that last guy on the list, the sulfuric acid, is a polyprotic acid because it has more than one proton. So it has many protons, in this case 2. So as a polyprotic acid, those 2 protons, they dissociate one at a time. So I've got sulfuric acid listed as a strong acid, but in reality only the first proton dissociating is a strong step. So those 2 equations I have listed there, the H2SO4 and the water dissociate, so left to right arrow, reactants go to products completely. So H2SO4 completely breaks apart into H plus, which we know in water becomes H3O plus, and hydrogen sulfate, so HSO4 negative 1. So putting sulfuric acid in water, it immediately breaks apart into H3O plus and HSO4 minus. That's strong acid, dissociates 100% of the time. Now the interesting part comes in with hydrogen sulfate. So that hydrogen sulfate ion itself is a weak acid. So it still has a proton, a hydrogen ion, that it could donate. And it does so, but hydrogen sulfate is not one of the strong acids. So when hydrogen sulfate donates its proton, which is what's happening in that second step, notice there's an equilibrium arrow, a forward and a backward arrow. Hydrogen sulfate is a weak acid, so it doesn't follow the same set of rules as the strong acids. It does not dissociate 100% of the time. So sulfuric acid is a strong acid, but it's really only the first proton being dissociated as a strong acid. So he's kind of special. Okay. So the term strong electrolyte is something that dissociates 100% of the time. So clearly strong acids are strong electrolytes and exist completely as ions as long as they're in aqueous solution, so as long as their solvent is water. So that's where the statement that I made earlier, that for a monoprotic, so those first 5 strong acids, their molarity, that's what the brackets are indicating molarity. The molarity of the strong acid is always going to be equal to the molarity of the hydronium ion concentration. This is important if we're trying to do things like solve for the pH, where the pH equation is the negative log of the hydronium ion. Okay, so that statement's for the monoprotic strong acids. For sulfuric acid, that was the interesting one. Remember, the first proton, the first hydrogen being dissociated is 100% of the time. So H2SO4 becomes HSO4 minus with the H plus, the proton. The second step, though, is not 100% of the time. The second step has an equilibrium constant because it goes to equilibrium. I just have the equilibrium constant listed there. It's 1.0 times 10 to the negative second. As far as equilibrium constants go, that's still relatively high. So hydrogen sulfate is a weak acid, but it is a strongish weak acid. How's that for wonderful scientific terminology? All right, so switching over to the bases. There are 6 strong bases: lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium hydroxide, cesium hydroxide, and then this what looks like R4NOH. So the R's, those are representing some carbon group. So that could be like a methyl group or an ethyl group. So it's nitrogen with 4 bonds, all to some carbon group thing, bonded to OH. So it's an ionic bond, OH minus, with that NR4 in front of it. So these are all strong bases, meaning they dissociate 100% of the time. All of them only contain 1 hydroxide ion. So the molarity of any of these 6 strong bases is going to be equal to the hydroxide ion molarity, because all of them will dissociate completely into their positive charge, which differs for each of them, and then OH minus. So all these 6 strong bases, their molarity is always going to be equal to the hydroxide ion molarity. So we're just going to practice using this information in some calculations. So again, usually when we're dealing with acids and bases, we often need to know the pH of that solution. So in this example, we need to calculate the pH of a 0.025 molarity solution of hydrochloric acid. Well, hydrochloric acid is one of the strong acids. So what that tells me is I know that the molarity of HCl, which was given in the problem to be 0.025. I know that that is going to be equal to the hydronium ion molarity, because strong acids dissociate completely. Okay, so I now know the hydronium ion molarity is 0.025. Well, the pH equation that we learned earlier in this chapter, pH equals the negative log of the molarity of hydronium ion concentration. So we have enough information to solve for pH. So using this equation, so I'm solving for pH. And then for the hydronium ion concentration, I'm just going to enter 0.025. So I plug this into my calculator. We have to follow the sig fig rules of logs, which when we're dealing with a base 10 log, the value inside of the log, its number of significant figures, which in this case, 2 sig figs, 0.025 has 2 sig figs. That's going to result in the same number of decimal places to the right of the decimal point. So what I got on my calculator, like 1.60206 kind of thing. So in terms of sig figs, 2 decimal places, or 2 sig figs, sorry, so 2 decimal places to the right. So the 1.60 are my significant figures. I'd keep the 206 just because I don't want to round yet, but those are not significant. So that's me solving for the pH of a specific molarity of hydrochloric acid. So let's just do it for one more strong acid. So this time I have a 0.105 molarity solution of nitric acid. Okay, so again, I know the molarity of HNO3. .105. Okay. since nitric acid is one of the strong acids, we know it dissociates completely, so it dissociates 100% of the time. So the two things it dissociates into are H+, which we know in water becomes H3O+, and then it also dissociates into nitrate ion. So actually the molarity of nitrate ion is 0.105. That's just not useful to me in this example, okay? Because in this problem we're trying to solve for pH. Well, the equation for pH, negative log of H3O+. Well, since we determined that we know what the molarity of hydronium ion is, I'm just going to substitute that number into this equation. So the negative log of 0.105. So I'll type this into my calculator. The molarity inside of the log has 3 significant figures, so my answer should go to 3 places to the right of the decimal point. So what I got on my calculator, 0.978, keep a couple digits, 81. So 3 places to the right of the decimal point because of 3 significant figures. So hopefully we're feeling good about determining the pH if I know the molarity of one of the strong acids. I didn't do an example of sulfuric acid, since with sulfuric acid it's kind of a mix of strong acid and weak acid, and this example, or this only goes through strong acids and strong bases. So let's practice with the strong bases. So for this one, we have a 0.0447 molarity solution of sodium hydroxide. So I know the molarity of sodium hydroxide is 0.0447. Well, sodium hydroxide are one of the 6 strong bases that was listed, so I know that dissociates into Na plus and OH minus completely. So all of the sodium hydroxide is now Na plus and OH minus. Of those 2 ions, the one that is most helpful to me in determining pH is hydroxide ion. Okay. So the way I would approach this, if I'm trying to solve for the pH, well, I don't have the hydronium ion, the H3O plus molarity. I have the hydroxide, the OH molarity. So I would use that OH to determine the POH, which the equation is the negative log of the hydroxide ion molarity. And that is useful to me because I also know the equation pH plus POH equals 14. So if I can determine the pH, I can get the pH by just subtracting from 14. So that's the approach that I would use. We also know that the hydronium ion molarity multiplied by the hydroxide ion molarity equals Kw, the equilibrium constant of water, so 1.0 times 10 to the negative 14th. So your other option is to take that hydroxide ion molarity, substitute it in here, solve for the hydronium molarity, and then plug it into the pH equation. So that's one possible route. I'm going to go the POH route. So I'm going to take the POH equation and plug 0.0447 in as the hydroxide ion molarity. So when I plug this into my calculator, that molarity has 3 sig figs. So my POH will go 3 places to the right of the decimal point, so 1.34963, keeping a couple extra digits. So the 693 are not significant. Well, that is my POH value. But if I want to solve for the pH value, I'm going to have to use, that's a beautiful star, that equation. So I'm going to take 14 minus 1.349693. So what I'm going to end up with here is 12.650. Going 3 places to the right of the decimal point. I'm just going to keep 308 along for the ride. So that would be the pH of this 0.0447 molarity solution of sodium hydroxide. Definitely basic, as the pH is way higher than 7. Alright, one more example of a base. In this one, we've got a 0.0700 molarity solution of lithium hydroxide. So I know the molarity of lithium hydroxide 0.07. Since lithium hydroxide is one of the 6 strong bases, I know it dissociates completely. So it dissociates into a 0.0700 molarity solution of lithium and a 0.0700 molarity solution of hydroxide. So again, I'm trying to solve for pH. I'm going to follow the same approach as the last one. I'm going to use this information to solve for the pOH and then convert it to the pH. So there's my pOH equation. So I'm going to substitute 0.0700. Plug this into my calculator. The molarity has 3 sig figs, so I'm going to go 3 places to the right of the decimal point. So 1.154. I'm going to keep a 902 along for the ride. To convert this to pH, I'll subtract this from 14. So 14 minus 1.154,902. So I end up with 12.845. In terms of sig figs, that's all the sig figs. And what, like 1. Okay. So that is calculating the molarity of a strong, or using the molarity of a strong base to calculate the pH. All right. So the next video is going to be over weak acids and weak bases.